Okay. So now I'm going to talk a little bit more about the particular strengths of acids and bases and how they differ from each other. So this is where the idea of equilibrium is important. And now you'll understand why I went through all that with equilibrium and why we had to, look at equilibrium constants and all these things. Okay. Strong acid, you may hear the term, in fact, I'll throw the term around a lot, strong acid, weak acid. It may not be what it sounds like. You may think of a strong acid as something that can really burn through things, kind of thinking like movie acids or things. Not really. Really what it has to do with is equilibrium. So remember, equilibrium, if you have A plus B produces C plus D, right? It just means that the reaction is going to reach some equilibrium, at which point the reaction won't proceed any further because the rate, the forward rate and the backwards rate are the same. And so something with a really high K, big value of K, at equilibrium goes really far and has a lot of products. If it has a small K, it has a very few products and mostly reactants. So a strong acid is one that actually transfers 100% or nearly 100% of its protons in water. So in water, these are things that have equilibrium constants that are enormously big, effectively infinitely large as far as we're concerned. And in fact, we actually write these, like HCl is a strong acid. And so it reacts with water, and I only write a single arrow for it. I only write a single arrow because there's no appreciable backwards reaction. It only goes forward. I never have any intact HCl molecules, only chloride and hydronium. A weak acid is exactly the reverse. It's one where an equilibrium is established. It has generally a pretty small value of K, usually 10 to the negative third or less. Now, there's a wide range. Weak acids can be weaker than other weak acids. Weak acid is a really broad term. So acids can be stronger or weaker depending where their equilibrium lies. However, understand that the term strong, something we call a strong acid, is specifically for something that donates 100% of its protons. That basically donates 100% of its protons. It goes all the way to the right. A weak acid is anything that establishes an equilibrium. Okay? So, an example of a weak acid is acetic acid. So, it's going to react with water, and I'll get C2H3O2 minus its conjugate base, and hydronium. But what's important, what's different here is, where with a strong acid like HCl, you have no, when the system reaches equilibrium, there is no HCl intact in the water anymore. It's all this, all product. Acetic acid has a lot of intact acetic acid molecules. It has some hydronium and acetate, but mostly it has intact acetic acid molecules. So we'll actually, an acid, a strong acid is an acid whose equilibrium position is very far to the right, and a weak acid is one who's as far to the left. Okay. Same for bases. Strong base is one that reaction with water is complete. Weak lies far to the left. Hydroxide, OH minus, reacts completely with water or any acid. So OH minus, you put it in water, and bam, it reacts completely with the water, or any acid at all. So if you have any acid, it'll react as well. Okay, so any soluble hydroxide is a strong base. Most other bases are weak bases. So strong bases are easy to identify. Sodium hydroxide, calcium hydroxide, anything hydroxide is a strong base. Okay. Before I move on, I will say this. There are 7 strong acids that you will need to know. There are 7 of them. 3 of them are pretty easy to remember. HCl, HBr, HI. So all of the acids from the halogens except for fluorine. Fluorine is a weak acid. Also, H2SO4, HNO3, HClO4, and HClO3. These are the 7 common strong acids. They dissociate completely. Now, I should make special mention of sulfate. Only the first dissociation is complete. Only the first dissociation is complete. After that, it actually becomes, the second deprotonation is actually, the second deprotonation is weak. Right? The second deprotonation is weak. So this first one is strong, but the second one is weak. Okay. So now I'm going to talk a little bit specifically about weak acids. Now, all right. Here is a generic reaction for any acid. So you have acid reacting with water to make its conjugate base and hydronium. So let's look at this. Let's write the equilibrium expression for this reaction, right? Remember, products over reactants. So equilibrium concentration of conjugate base times equilibrium concentration of hydronium over equilibrium concentration of intact acid, and I omit water because water is a liquid, right? You always omit the liquids. So, I actually have this on my slide and I don't want to double up on it. So here it is. So what this tells you, Ka, now the A just means acid, meaning it's for this specific kind of reaction. It's specifically for an acid dissociating. What this means is the value of Ka tells you what the concentration of dissociated acid and hydronium are compared to the intact acid. Now, the kind of little secret here is hydronium is what really gives acids their acidic property. So we call something that has a higher value of K stronger because it produces more hydronium, right? So that's really what it is. The acid ionization constant, or the Ka, tells me how far to the right this equilibrium lies. Strong acids are infinitely large, all the way to the right. But we can have any balance here between the two. It just so happens that I happen to know that for acetic acid, so for the acetic acid dissociation, the Ka is 1.8 times 10 to the negative fifth. Pretty small, but it's definitely still acidic. Base ionization constant is going to be exactly the opposite, right? I can write pretty much the same thing. Kb is going to be the conjugate acid times the hydroxide over the intact base. I'm not going to really saddle you with numbers on this, but I am going to talk about things sort of just in general terms of strength. But the one last thing I really want you to know, the thing I think is important to realize. Okay, so the stronger, so if I have an acid, so HC2H3O2, and it's going to react with water, right? And I get C2H, stupid mouse, H3O2 plus hydronium. Remember that this reaction goes backwards, right? So, the more that this proton wants to leave the acid, you know, like, so for like HCl, it's very strong acid. The reaction goes completely, right? The hydrogen doesn't want to be attached to that chlorine at all. It would much rather go with the water, right? So, think about it this way. Let's think about it in the reverse terms, going back the other way. So, this HCl is really strong. The equilibrium lies all the way over here. The acetic acid, it's kind of in the middle. It's 10 to the negative fifth. It's not really a very big acid dissociation constant. So, and I forgot my charge here. minor detail. But let's think about acetate versus chloride. Which do you think is a stronger base? Acetate or chloride? Well, let's think, to figure this out, we got to think about it in terms of this. Something being a strong base means that it's going to take the proton very well away from something else. This was a strong acid, meaning the hydrogen doesn't attach well to chlorine. So therefore, this is not even really a base at all, right? This, however, is going to be a much stronger base because this bond is clearly stronger because it's harder to break apart. What I'm getting at here is that the stronger an acid is, the weaker its conjugate base is. And the weaker an acid is, the stronger its conjugate base, and the stronger a base, the weaker its conjugate acid, and vice versa. All the way up to, if something is a strong acid, then its conjugate base isn't even a base at all. Chloride isn't a base. However, HF, so I'm just going to swap these out here, HF is definitely a base. Or, I'm sorry, HF is a weak acid. So, fluoride is a base. Now, I'm just going to see if I can look it up here. So, the Ka for HF is 6.8 times 10 to the negative fourth. And the Ka for acetic acid is 1.8 times 10 to the negative fifth. Okay, so here's the deal. So HF and HC2H3O2, which is the stronger acid? HF is a stronger acid because its Ka is larger. Which is a stronger base? This. If this is the stronger base, the stronger this is, the weaker its conjugate base is. The weaker this acid is, the stronger its conjugate base. One last quick definition before I end this particular video is salt. Okay. You've probably heard me say this before. When I say salt, you probably think of sodium chloride. When a chemist says salt, they don't mean sodium chloride. They mean any ionic compound. They mean an ionic compound. That's all they mean. So hang on to that, and then we'll pick up with talking about neutralization reactions in